Today, I have Pravir Malik on the show. This is one of the most in-depth, thought-provoking, deep interviews that I've ever had in my life. If you don't know much about me, I have been podcasting since 2010, was one of the first podcasts on Apple in their podcast platform back in the day when it launched. I actually was doing blog talk radio before podcasting, which was streaming virtually to a live audience via the internet. And then prior to that, I did radio. I have interviewed hundreds and hundreds and hundreds of leaders, world leaders, politicians, executives, inventors, investors, and very interesting people. I don't know if I've ever had a conversation quite like the one we have here today. I told my producers after we recorded it to try to make me look smart, because there's certain points in here where I get a little excited and even a little bit lost and confused about what Pravir is talking about. But I think it's so important to listen to this with an open mind. Pravir's opinion on, and I don't even want to say opinion, Pravir's theories on things like quantum physics and quantum computing might be controversial. I've seen some of the comments on some of the other videos that Pravir has been on. Some people don't like his style. They don't like his approach. Why? Well, you'll hear in the next coming minutes. Pravir has a worldview and a perspective and a theory after writing 22 books on quantum and these topics, light, cosmology. He has a very deep understanding of these topics and a belief that sometimes flies in the face of the normal convention of the scientific community. I embrace those ideas because I want to hear differing and altered perspectives from those that are coming through mainstream science. I think this is one of those episodes that's a little different, and there's a few more coming in the pipeline that are a little different from the things we've done in the past where we've featured a product or service and we've talked about its utility. This is truly rethinking the physics of the universe and better understanding how we may need a new model. I even say in the show, we have hundreds of biases. And a friend of mine, I told this to, I said, we got a lot of biases. And he said, no, we don't. We have the wrong model. We need to throw out the models that undergird the way we think about healthcare and education and physics and science and in the world. We need to throw the models away. And we need to look at the data again and come up with new models based upon what we know now. Now, we should compare those to the old models and see how close they were, because we might find that there's wisdom there, there's knowledge there, there's understanding there that maybe we just have lost or we don't have any more today. But I think it's really important as an executive, as a leader, as a scientist, as a person who has influence, to truly lay aside your own beliefs. And here's something different. You're going to get that today. This one delivers. The next two episodes with Pravir, I think, will be very thought-provoking and exciting. I'm excited that the gentleman who introduced me to Pravir also has agreed to come on the podcast, Michael Hrushka. Michael and I go back 30 years. We've known each other more than 30 years, came back from the music scene in central Pennsylvania in the early 90s. Mike is a leader in AI development right now and AI learning. And I think you'll see in the episodes coming up with him over the few weeks after these with Pravir, we're going to go real deep, real fast here. So hold on to your seats, folks. Pay attention. Here's my first part of the interview with Pravir Malik. Hi, everybody, and welcome back to another edition of The Convergence. I am so excited about today because I've talked about quantum computing. We've talked a lot about AI, and today I've got a real expert here with me, Pravir Malik, author of 22 books on these topics. I couldn't have asked for a guest that knows more about these complex, deep thinking subjects. Pravir, thank you so much for being here with me today.
Oh, Derrick, it's a complete pleasure. Thank you. I'm looking forward to this conversation, and it's the things that you bring up, like complex systems and quantum and AI. That, to me, they're all part of one kind of package. So I hope that our conversation will dive into that in a little more detail. So
Absolutely.
Yeah.
Pravir, tell me a little bit about your background. I mean, you have been a researcher, you've been a scientist. You definitely are the source. You got to go to you to get the answers to questions. Tell us a little bit about that background and your journey to this point of talking about these types of things.
Sure. So I started off in the field of computer engineering. So essentially, my degree was in computer engineering and then computer science. I did a graduate degree in artificial intelligence. That was a long time ago. And then in the early 90s, when I got into the workforce, I was a programmer doing expert system stuff and robotic stuff. And the biggest question or the biggest complexity I faced is, hey, when I write code, it works perfectly, but the organizations never work perfectly. And so what really drew me was, why are organizations so complex and what's the real dynamics behind it? And that's drew me into the field of essentially systems thinking and complexity. And I began to take a very deep dive into complexity. I ended up doing a PhD with looking at the mathematics of innovation and complex systems. And essentially, that's what also led into in that discovery for what's driving resilience in systems. I was led into biological systems, into chemical systems, into physical systems, into the nature of light. And that's how I got interested in quantum. And then I began to, the last decade, I spent a lot of time thinking about quantum in general. And a lot of the books that I've written are my take on quantum theory, but from the point of view of light. So I call it a cosmology of light. And I've got 10 mathematical books over there. And I've collaborated with some artists. So 6 collaborations with artists to take those esoteric concepts and try to illustrate them with something that's more down to earth and what people can viscerally connect to. So that's, in a nutshell, been kind of the trajectory of my journey.
Well, I love that too, because as we talked about a little bit before the show, I've been working in in operations world for a long time and working with change inside organizations. And I have this new book, Adaptagility, that is all about the biological resistance that human beings have to change and how we can realign that and bring limbic resonance into organizations so that people's systems synchronize so that they don't have to respond like they're, is a cave bear, approaching us when we think about change. I'd love to talk a little bit. I mean, you mentioned fractals too. I'm a huge, I usually have the book laying here. There's this great book I found called Math Numbers. I don't understand half of it, but it's just so cool because they get into fractals and they get into all of these different things. Maybe you can explain a little bit about what fractals are. They sort of blew me away when I discovered what fractals were and how math can be turned essentially, I mean, in a lot of senses into art, because it is incredibly beautiful experience to watch a fractal calculation, I don't know what the right word is, but play out into its infinity.
Yeah. So the simplest way that I think about a fractal is from some common examples that we come across every day in life. But the food that we eat, for example, like a broccoli is a perfect example of a fractal. And that's where you've got the shape of the whole broccoli that's repeated, or you can see the same shape in the stem. You can see the same shape in the brocklet. And that gives you an insight into nature's a tremendous ability to design efficiently, because it's taking a construct, a mathematical construct, and then repeating it on different scale to create this complexity. And we find that kind of approach in lots of different physical instances. What really drew my attention was, can we apply that same kind of thinking, or can we see similar patterns in behavioral systems? So, of course, there's been work also on stock markets, which is in a sense behavioral, but it follows like a physical trajectory.
Sure.
So, so for example, we know that when greed rises, then there's going to be an upshoot in the market, and then at some point it turns to fear, and there's going to be a downshoot, and this kind of repeats itself, and that's you're getting from the physical to behavioral. But I was much more interested in how can perceptions, assumptions that people have influence how organizations are run and how organizations go to market. And that was my specific interest in trying to put together a fractal theory. So I ended up writing 3 books. These were published by Sage, so it was a fractal series on really a theoretical approach to fractals applied to
Right.
complex behavioral phenomenon in a sense. So.
So we're talking about thinking about something like the Fibonacci sequence, right? That we see a lot of these patterns in nature, and essentially what you're saying is let's apply that a little bit to behavioral psychology. Am I getting that right? That it's like maybe there's a little bit more beneath the surface. I think it's interesting too, because I do believe that many times we don't realize that we are animals, you know, at the core. I'm working on a presentation in my other browser for a CEO group tomorrow, and I'm showing the Kubler-Ross change curve of how change works inside organizations. And then after the next slide, I show people the other thing that Kubler-Ross did, which is the exact same curve, which is the acceptance of the death of a loved one, the 5 stages of grief. It's exactly the same as how people respond to change inside organizations. So to your point, there is evidence that biology mimics this and psychology mimics this as well.
Yes, absolutely.
Yeah. That's great. Let's talk a little bit about complex adaptive systems here, because I think that's the root of where this comes from, is thinking about what are complex adaptive systems, I guess would be the first question for you here.
Yeah, so broadly speaking, it's a system that which displays complexity. And the way to think about complexity is that I would differentiate it from a simple system or a complicated system. A complicated system has a lot of different parts, and there's definite mathematics to understand it. And that, of course, is way more complicated than a simple system. But a complex system is where there's emergence happening because you don't necessarily know, due to the interaction of different parts, what's going to arise from there. So that's, to me, a definition of complexity where the whole may be way greater than any way that you look at the parts. And there's something happening that you couldn't have predicted. You know, for example, a very concrete way that I think about it is that at some point you had the universe that was just animated by atoms.
Right.
And then you couldn't have predicted that from those atoms there would be molecules that would be created, and from those molecules you'd have molecular plans that would create living cells. There's no way by just looking at by atoms or molecules that you could have predicted the emergence of complex life, which had a bunch of molecular plans that animate every living cell. You can't, from just looking at the system the way it is, predict complexity. So complex adaptive systems is something that has that emergent quality and also can completely adapt in a more than a resilient way, because as threat comes to it, it utilizes that threat in a positive way to become greater than the threat itself. I mean, that to me is what a complex adaptive system is.
I love that. Let me dig a little deeper on that for a moment, because I know where we want to land here is talking about AI. And I wrote this down just the other day, and I'm so glad that you brought this up, because I asked myself this question: is complexity subjective? Right? Are we looking at complexity and saying this system is very, very complex because the limits of the human mind won't allow us to understand that? But a super, intelligent AI might look at that and go, not complex at all. This is it's a very simple system of 1 + 1 = 2. And we're going, yeah, that's a little bit outside the computing power and range that we have as human beings. Do you believe that is the case, that there is some subjectivity to that when you're thinking about super intelligence?
Yes, surely, because anything that we habitually begin to see is due to objectivity.
Yes.
And subjectivity gives us a vertical dimension, which, when we think about objectivity, it's more like a horizontal dimension by which we are parsing the world around us. But when we think about the vertical dimension, it's essentially this axis of subjectivity where a deeper or a different view can help us see the same thing completely differently. So, in your example that you brought up in the book that you have, Adapt Agility, and the limbic response to change, when we started this conversation, we also know that if we step outside of a limbic response and if we begin to see the same situation from higher in this vertical axis. So maybe by using reason, for instance, then that opens up a whole bunch of possibilities that didn't exist before. So I'll just pause there. But that's
Yeah,
what I'm
no, I
talking
think
about.
it's a really interesting point. And I think it is true that if you look at, our evolution as a species, particularly in the last 5 or 6,000 years, we had limitations on our understanding of things. We had blinders on in a lot of senses. And now we're getting to a point where some of those blinders are coming off, and maybe they're coming off a little too quickly. I think we do have to remember that from a biological perspective, we as humans are not evolved for this environment that we currently live in. I mean, so it's going to take a little time for us to catch up. But I think it's a really valid point, and I don't think I've ever thought about it from the objectivity of horizontal and the subjectivity of the vertical. I love, there's a book that was written in the late 1800s called Flatland by a guy named Edwin A. Abbott, and it's one of my all-time favorite books because it is written by a two-dimensional square that lives in a two-dimensional universe.
Yeah.
And he explains all the rules and how people get married in their homes, and you're like, and then he experiences a three-dimensional object, and he's like, this is crazy. The big spoiler to that whole book is the end when he says to the three-dimensional cube, it must be really cool to think that there's probably a four-dimensional object out there. And the three-dimensional object is like, you jerk, get away from me. I can't imagine such a thing. Right? It's like, It just goes to show that our perspective is so influenced by what we see. And I'm excited about talking about these next kind of couple parts, because I'd love to talk about quantum, but I don't want to forget to. I want to get into this cosmology and light thing because I'm understanding now the foundational structure of how you, Pravir, have put this all together, and I'm starting to see where you're going. So maybe let's talk about quantum let's talk about that quantum piece, because that's another piece that you've been an expert in. I don't know if many people understand what quantum computing is. Would you mind maybe giving us explain it to us like we're fifth graders, response on what a quantum computing system is?
So the simplest way to think about quantum computation is that it's essentially a device or a computer that takes or that can generate different quantum phenomena. And what do we mean by quantum phenomena? So, we've heard popularly words like entanglement or superposition, annealing, tunneling. So the way that I would describe a quantum computer is a quantum device that can actually create these quantum mechanical processes of entanglement, of superposition, of annealing, of tunneling. And that's really what a quantum computer is. So if you can create something that consciously creates entanglement or that allows superposition to take place, that's a quantum computer.
You used the word consciously there for a second. I think consciously is on our part, right? Not on the computers, or at least I hope not.
Right. I mean, so, of course, there's a couple of things, and let's see how far or how deep we get into this quantum idea or the quantum realm. So, that's a definition of quantum. But if I were to take the kind of spin that I have on it, so, if we look at mainstream quantum computation, then essentially it was originated with the Nobel laureate, Dr. Richard Feynman, who is considered to be the father of the quantum computing industry. He kind of posed a challenge for basically the computing industry that we need to create a computer that's radically different and that leverages the quantum mechanical processes of nature in order to compute. And so that was his challenge. And essentially, the trajectory by which the quantum computing industry has evolved is that it has locked into these definitions of what superposition is, what entanglement is. And it's essentially, without proving that any of them exist, it's assuming that they exist because, we can go back 100 years to Copenhagen interpretation of quantum mechanics and superposition and entanglement being a part of them. And there's a particular interpretation for how superposition acts and entanglement acts. And all quantum computers essentially aim to replicate that or assume that it exists. And that's how the quantum computing industry has evolved. Now, I'm going to pause there before I suggest why I challenge that and a different approach to it.
I'm okay with. I love that because I think you've just hit on something. I mean, to summarize that, it was just because it works doesn't mean it exists. I mean, it's and I think that's a very important point. I think we could go back to mythology. I love telling people. Odin said he would slay all the ice giants. I don't see any ice giants around, so obviously Odin knew what he was doing. Well. That's some assumptions there that I don't need to completely make. And I think it's the same thing here is we've made some assumptions in quantum computing based upon, theories that were 50, 70, 500 years ago, and they work. But that is not evidence enough that they are correct. We've got to dig deeper to find out for sure if those things were correct. And we have to be open to other theories that may be a little bit different than that.
Yes, and even the question of whether they work, because there's there's certainly applications. Quantum theory has proven without a doubt that it works. The issue is quantum computation, which is radically different from quantum theory. So if I were to think about quantum theory, it's essentially has to do with how an atom, say, responds to light, and how the different quantum particles inside an atom can get manipulated by light, and that quantum theory is without a doubt it exists. I mean, so all the complexity of chemistry and so many different applications that we have, from computers to cell phones, are driven by that basic foundation of quantum theory. So there's no question about quantum theory. The question is about our interpretation of quantum computation in today's kind of rendering of it, because we are assuming, just as quantum theory has proven itself without a doubt, we're assuming that the basis of quantum computation, which is entanglement, superposition, and interpretation of a probabilistic nature, are also entirely and absolutely true. Right, but there's two separate things.
Can you talk about that a little bit more? I mean, what is quantum computing in that regard? Then, what is quantum computation? I understand it very basically from a basic understanding of entanglement and superposition, but maybe you can explain that a little bit more, because I don't think I totally thought of them as separate things. I thought of them both as the same.
No.
Okay, good.
So there's without a doubt, there's validity to quantum theory when we think about quantum theory as that, where the atom is the basic structure, and the atom is a perfect example of a quantum computer, because it has all the quantum particles that we know of existing within it. It's got bosons, leptons, quarks, and the Higgs boson that creates mass. So you've got all those quantum particles. We know that if we throw light into an atom, that an electron can jump to another superposed state. So we've got superposition as well. We know, for example, that if you got an atom of silver, which has an atomic number of 47, that there's automatically entanglement with all atomic numbers 47, because silver behaves the same way no matter where it is. Right?
I was not aware of that. Okay, that's very interesting. I hadn't thought about it from the periodic table perspective, that there is a entanglement element solely because of the atomic structure.
Yes,
is that right?
That's my interpretation of it. I mean, that's how
right. Yeah, of course.
Right. So entanglement and superposition are natural phenomena that exist already. Now, there's no kind of mystery to creating it. They already exist. So when we talk about quantum computation and we say we're going to leverage the properties of entanglement and superposition to create these massively powerful quantum computers, the fact is that, first of all, you've already got these quantum computers that exist and already work by entanglement and superposition, and an atom is a perfect instance of that. Right? So you already have a quantum computer that's showing entanglement and superposition. But what we're talking about when we talk about quantum computation is a different kind of superposition and a different kind of entanglement. And this goes back to the way that quantum theory has been interpreted. So we've got the Copenhagen interpretation of quantum mechanics that is perhaps the most popular version of how that the weirdness in the quantum world works.
Yeah.
And the idea there is that you've got, before you measure something, so you can, before you measure a quantum object, it can exist in infinite number of states.
Yeah.
Right. And that's that when we think about superposition, that's really what we're thinking about, because we're saying that that thing before measurement exists in so many different states, and we want to leverage that property to create massive advantages in the way that we calculate. So we can, and that's the theory behind quantum computation, but that's in fact not how superposition works, right? I mean, so if we look at the existing evidence of superposition, the concrete evidence we have is how an electron can go to superposed state in an atom. That's where we concretely can see it being displayed. It's fundamentally different from the electron being in a million different states and then precipitating into a single state. So that's an interpretation we've created that is not necessarily how computation actually works, right?
And you've got a belief on how computation works that is associated with light. Is that correct?
Yes. So I'm going to talk about that now.
Please. I don't want to get ahead. I'm fascinated by this.
So this is where the idea of complex systems, or seeing everything as a single system, drives to what really might be possible with computation. So, one of the approaches that the industry has taken today, the quantum computing industry, is to look at phenomena like superposition and entanglement in isolation. So they're trying to create it in these mechanical creations that are called qubits. Okay, so these electromechanical creations that are supposed to encapsulate the infinity of superposition, and then are supposed to also be able to create entanglement at will. That's the idea behind quantum computation. But however, now my point of view is that matter and life have emerged from the quantum levels. And just bear with me for a minute. Okay, so they've emerged and it's part of a single system. So if we truly want to understand, not based on our interpretation, but if we truly want to understand what's happening at the quantum level, what we have to do is we've got to look at how matter and life emerge. And here, let me get concrete. What do I mean by matter and life emerging? So when we look at how quantum particles emerge, we look at how atoms emerge. At the level of life, we look at how molecular plans emerge. We can see that there's a similar pattern to their emergence. If we consider them to be part of one system, then we can see that there are only four molecular plans that exist in any living cell. We call them nucleic acids, polysaccharides, lipids, and proteins, but they have meanings. Nucleic acid, is carrying forward the knowledge in a cell. It has to do with knowledge. When you look at lipids, it creates compartments and so creates harmony in a cell. So it has to do with this thing that we call, this concept called harmony. When we look at polysaccharides, it has to do with the concept of energy because it provides energy for the cell. And we look at proteins, they're like the workhorse elements of a cell. There's like 30,000 different proteins in a single cell.
Yeah.
So now that's giving us insight into a pattern. So we're saying that this pattern that manifests as lipids, proteins, nucleic acids, and polysaccharides is actually something that we can approximately call knowledge, power, service, and harmony. That's the concept behind it. But we'll see the same thing going back, looking at this as a system. We'll see the same thing exist at the level of atoms. So, all atoms can be categorized as S shell, P shell, D shell, and F shell. Okay, and essentially, if we look at S shell atoms, it's stuff like hydrogen and helium. We know that that's the stuff that creates nuclear fusion. So there's a lot of power associated with that. When we look at D shell atoms, they're like your industrial workhorse elements, like iron, nickel, cobalt, aluminum, so forth. We use it for infrastructure. Right. So, we're seeing a similar pattern. And then when we look at P shell, we see stuff like carbon and silicon in there, which we can intuit has to do with knowledge in a certain sense, and we look at F-shed atoms, these are like massive experiments of collectivity at the atomic level, because you've got atoms of, atomic number of 108, which is huge for an atom. And so we're seeing this similar kind of concept of harmony. So the point being that when we look at nature as a single whole, we can see that there's a pattern that emerges at the molecular plant level.
Right.
There's a similar pattern that already emerged at the atomic level. If I drive back to quantum particles, we've got quarks, leptons, bosons, and a Higgs boson. I can make the case that since quarks entirely makes up a proton, and we know that proton is responsible for the atomic number, and once you know the atomic number, you know the behavior of an atom. So I can drive back and say that, hey, quarks are actually this thing that are carrying knowledge. Similarly, when you look at leptons, an electron is a perfect surrogate of a lepton, and we know that electrons are responsible for all the energy release, for the energy capture. So essentially, it's a carrier of power. So and bosons are a carrier of harmony. Higgs boson is a carrier of presence or service. So I can see the same pattern emerging as matter and life emerges.
I'm really fascinated by that whole thing. I mean, in a lot of senses, I mean, we've and I know there's even some investigation now into storing, data in DNA, right? And
Absolutely.
And thinking about the quarks as essentially the data storage of atoms. So, I mean, really, you're talking about a theory that brings together all aspects of physics and says quantum, Newtonian, whatever it is, it's all really part of one natural system.
Yes. So not just physics, but physics, chemistry, biology. Because when you think about physics, you can think about that layer of quantum particles and atoms and the electromagnetic field, right? So that's what physics is concerned with. When you think about chemistry, you're looking at atoms and kind of how they combine together to molecules and how molecules interact. And that's a layer of chemistry. And when you look at the layer of biology, then you've got the molecular plants and cells that entirely tell you all the biology of that exists in the cells, and cell will give you the biology of a species and so on. So what you're really saying is that biology, chemistry, and physics need to come together to give you insight into what's happening at the quantum level. So that's the point. My point is that there's a reverse extrapolation that you need to keep a hold of if you really want to understand what's happening at the quantum level. You can't just say that the quantum level has to do with that of some interpretation of superposition and entanglement. That to me, that's inaccurate.
Yeah.
What you've got to do is you've got to reverse extrapolate based on how matter and life, so how physics, chemistry, biology in their proof have emerged, drive it back and say that all this stuff is emerging from the quantum levels, and so it's giving us tremendous insight into how we need to think about and how we need to actually approach computation at the quantum level. It's completely different from the trajectory that is being followed today by the quantum computing industry.
Well, I think as a systems thinker, and we talked about this a little bit earlier, we look for that interconnectivity. I do a lot of consulting around systems, and I explain I did it twice today with CEOs. There's inputs to a system, there's outputs, there's outcomes. But most executives ignore the throughput, right? They don't know how the sausage is made. They know how it started, and they know where we are today, and they can project where it's going. But the real knowledge of the system is in the throughput. It is in how we assemble things together in order to get to the output that we're looking for. And I'm loving what you're saying, because I think it's the first time I've ever heard somebody that understands physics actually not break these into different segments, but to actually say it's all part of the system. This is the throughput. This is how all of these things come about. It isn't just, your product doesn't just magically appear in the customer's house. There's a lot of things that go into it, raw materials that are mined across the world. There's actually a great, somebody did a video one time about what it takes to make a pencil, and there's hundreds of thousands of miles of transportation and graphene and graphite and wood that was chopped down in forests and trucked across the world, and the paint, the eraser. There's so many things, but for some reason, I think you're right. A lot of people in the scientific community tend to stick to their own specialty, and they don't want to look outside of that.
Yeah.
Fascinating. Yeah, it's funny. I'm going to tell a quick story here. I have a family member who is who's been in the rocket science industry for many years, and he has told me on time and time again that when you get stuck on a problem, the best thing you can do is randomly select professors by the color of their socks. Just get 10 professors with brown socks in a room, explain the rocket science-y problem to them, and for some reason they come up with a solution. Why? Because they haven't at all attended the same lectures and went to the same schools and read the same books. They've got this perspective. And he's like, half the time it's the biology professor that teaches us something about, rocket fuel that we're like, wait a second, that can't be. But that's really what you're talking about, is this unified theory of bringing all that together.
Yes, exactly. And the point of quantum computation is that it's hubris to kind of say that we understand the quantum level, because we don't.
Right.
And to say that we are going to create quantum computers, how can you create a quantum computer if you don't understand what's going on at the quantum level? You can't, right? But we're saying we understand it, and we're saying that this is how it works, and it works by this interpretation of superposition, this interpretation of entanglement. And guess what? Nature's entirely random, so we're going to use probabilistic mechanisms in this computer, and we're going to bring this stuff together that we barely understand, and we're going to create a working quantum computer. It doesn't work that way, right? So it's simply not going to work.
I love that. So let's talk a little bit about that in the realm before we start talking about AI.
Yeah.
I mean, that has to be a little bit controversial. What you just said has to be a little bit controversial.
It is. Yeah.
I haven't heard this is a mainstream opinion, right? And I've talked to a number of physicists and I've heard their opinions on things, but there does seem to be a Chinese wall that they put up in between the different practices of physics and biology and chemistry. And they say, well, that's something different. And I think maybe it's because as scientists tend to think like doctors, and doctors are like, it is not my specialty. I'm not going to practice in that field because I'm not a podiatrist, right? I'm an oncologist. Do you think is this a cultural challenge in the scientific community that is causing this, or what do you think?
Well, I think there's a few different things. So certainly, of course, it's cultural, because that's the way that we've approached science in general for centuries, right? And certainly in the 20th, 21st century, that's how we've approached science. But it's also political. Because for instance, I can go back to the personalities of Einstein and Bohr, who, Einstein, we know, was instrumental in creating quantum theory over a century ago, along with Max Planck. And Bohr was, of course, created the vision of the atom, which was very, very insightful. Yes. But then when you look at their personalities, you got Bohr, who is apparently a very charismatic person who loved to have social gatherings, who kind of expressed his point of view differently. And Einstein was the opposite. He didn't do that kind of stuff. He was very focused on wanting to solve problems and think about things in a different way. And so you can see how the physics community has kind of evolved around these personalities, and essentially around Niels Bohr, because of his dynamism and charisma in general. And so there's a political element to it, because in a sense, if once the Bohr's view of which is the Copenhagen interpretation of quantum mechanics has become mainstream, it becomes academic suicide to begin to step outside of that. And academicians who did venture outside paid the price heavily, through the 20th century, and that's part of the reason why things are the way that they are. But really, if you go back to the origins, it's that's why I call it political. And then there's kind of funding that's been self reinforced. It's not really based on trying to get to the true answer or look at things objectively and figure out what's really happening at the quantum level. It's essentially, hey, I've got this interpretation that a little bit strengthens the Copenhagen interpretation, or it's in line with that. And so, yes, I'm going to get funding because it's in line with the mainstream. And that's how people have come to believe that funding should be dispersed right now. So there's other factors beyond. I mean, you can club them all into culture, but it's social, cultural, political, that have in a sense created, I think, our silo mentality and our inability to step outside of the areas that we've become to specialize in. But
Hey, I
again,
think you're so right.
That's my
Yeah,
point
no,
of
I
view.
think you're so right, and I think this happens in any practice of science. I've been chatting with a couple folks here recently that are doing research on psychedelics, and this was something that was a career ender 20 years ago, and there was no funding available for it. And now all of a sudden, people are starting to say, "Wait a second! Now major universities are researching this and finding out some very interesting information that is completely counter to the position that the scientific community had." But now all of a sudden it's become cool. And I think, I think part of that challenge is, we talked about the biological resistance to change earlier. The reality is the stories that have been passed down for thousands of years were passed down by the best storyteller wins.
Right.
What's the old saying? If what I think it says, if until the lion learns how to write, the story will always make a hero of the hunter, right? It's just the truth. I mean, until that becomes sort of a mainstream storytelling thing, it's really hard to do. And listen, I'm a big personality. I host lots of podcasts, so I know that that's true. You can sort of you can influence some things, and maybe in the wrong way, by being too charismatic. It's really fascinating to me where you're going with this, and I think the timing is really good as well, because we are emerging into this era. Obviously AI has been around for a very long time. I think I have gotten more phone calls on speaking to executives about AI in the last 60 days than I've ever gotten in my entire life. So obviously it's coming to the forefront. And so how do we, maybe let's pivot a little bit to talk a little bit about what AI is.
Sure.
Is there a quantum connection there in the future?
Yes.
And then I'd love to hear more about the cosmology and your light theory as well. So AI, tell me a little bit about what your thoughts are on the AI that we're seeing right now, and how that works, and where we're going with it. All right. So I am a little bit mind melted after that interview. I have to admit, I interviewed Pravir. We did this one and another one. I think we ended about 5 p.m. PST Pacific. I could not stop my mind from thinking all night. I think I was up till 2:30 in the morning and back up about 4:30 after this conversation, because it shook my worldview. I think in this first segment that you just heard, there's a lot of conversation about laying the landscape and the foundation for what's happening today. Next week, get ready, because it's going to go real deep, real fast in my part 2 with Pravir Malik.
Thanks for listening to The Convergence. If you want more information about the topics you've heard here today, reach out to us at theconvergencepodcast.com.